Hello. Good evening, everyone, and welcome to this very special lecture of the ICTS. As you know, this is an ICTS distinguished lecture to be given by Professor Dick Bond. I just wanted to say a few words about our special lecture series. The ICTS distinguished lecture is given by very eminent scientists in physics, mathematics, in a number of areas. In fact, we had another one sort of by coincidence almost. We had one by Professor Duncan Haldane, to which some of you came on Friday. But as part of the cosmology meeting, we have a number of special events, and we are starting it off with Professor Bond's distinguished lecture. As you know, on Thursday, we'll have the first Chandrasekhar lecture by Professor Sunyaev. And this weekend, there is a Copy with Curiosity by Francois Boucher. And finally, on the 22nd, there is the Vishweshwara public lecture by Lyman Page. So there are a number of activities lined up, and so I would encourage all of you to attend these, and especially the Copy with Curiosity. If you are interested in going to the city Sunday afternoon, you can drop by the planetarium, see the sort of atmosphere in that event, and then of course spend the evening in the city. So in any case, I won't say very much more. I'll hand it over to Shubha, who will give an introduction to the speaker.
Thank you, Rajesh. Okay, so it's a real pleasure to basically welcome J. Richard Bond, properly known as Dick to all of us, to give this distinguished lecture. Dick did his PhD under the Nobel laureate William Fowler from Caltech, and then he has been in the Canadian Institute of Theoretical Astrophysics, CITA, which is in the University of Toronto, for the last 33 years, of which 10 years as the director of CITA, and then 15 years as the director of the Cosmology and Gravity program of the Canadian Research. Now, as the director of CITA, the biggest thing that Dick, of course, has a huge contribution to all fields in cosmology. But I think, to me, the biggest contribution has been to make CITA to be one of the best institutes of cosmology in the world, through which many of us has passed. Dick has worked on almost every aspect of cosmology, from inflation to CMB, large-scale structure, data, theory, simulations, and also things that a lot of cosmologists don't do, which he very lovingly calls gastrophysics. So really working with the nitty-gritties of gas physics that goes into all this stuff. He, of course, has got this huge list of awards recognized for his work. I'm not going to sort of go through them, but maybe I should say a few. He got the Gerhard Herzberg Canada Gold Medal for Science and Engineering, the Killam Award, the Torrey Medal, the Queen Elizabeth Diamond Jubilee Medal. He also received the Medal for Lifetime Achievement in Physics from the Canadian Association of Physicists. He was bestowed with the Medal of the Officer of the Order of Canada. So that's a civilian award. And I know very few people who actually also gets one of the highest civilian awards of a country. And lastly, Dick is the only person who got the Gruber Prize in Cosmology not once, but twice. First for his work, and then in 2008, and then again in 2018 as part of the Planck team. When we think of Dick, very lovingly, I almost think that Dick is really not the Dick Bond, the James Bond of cosmology. I mean, his ideas have more potent than the real Bond's bullets. So with that, let me ask Dick to give this distinguished lecture on quantum inflation in the Planck era and beyond. Dick, it's all yours.
Before Dick begins, we have a small little ceremony. I invite Professor Varun Sani to hand over a memento on behalf of ICTS to the speaker. You can. It's a sandalwood Buddha.
Well, I'll read this back here. Right, so this is supposed to be a somewhat public lecture, but I am not well known for keeping the information flow down. You will learn all about the history of the CMB. You'll learn more from Rashid, who not obviously, but does go back a lot longer than I do, but I do go back a long way. And so I am going to take you through the cosmic microwave background past into the present, and the executive summary for cosmology is this thing that you, I think, all know really well, that we have compressed the huge data flow from space and from the various ground-based and balloon-based telescopes into 7 numbers, basically, that characterize the modern vision of the cosmological world. I'll also talk about the future, and our hope is to go beyond those numbers into beyond the standard model of cosmology, the tilted lambda CDM model, to get something more out of it beyond the standard model of cosmology, just like particle physicists wish that they could find something beyond the standard model of particle physics. Of course, they have. That's the dark matter, but it is not yet clear how it all fits in. Along the way, though, I'm going to make sure that my illustrious professorial friends in the audience will be at least marginally entertained by the latest of our thinking, or my thinking anyway, about inflation in the early universe, which is I look at things in a rather different way than most people, and I hope that you will catch some of that vision. So first title here is From Complexity to Simplicity to Complexity to Simplicity, the Universe at Large. The ultra-early times will presumably have been highly complex, with huge mountains and valleys of high density contrasts, bubbling, tunneling events. But the patch of the universe that we can see, our Hubble patch, which as a theorist I find just so constricting in one's day-to-day, no, it's such a large thing, the universe. But anyway, it is simple. That's the basis of the 7 numbers. But then the natural evolution under gravity, gravitational instability, leads to complexity, the complexity being the cosmic web. But since it grew out of simplicity, it is quite understandable. And then if we look to the far future, at least what we can forecast now, if we go back to a high degree of simplicity where dark energy is the dominant driver of the evolution, and not really that much happens. Of course, there could be a surprise. I doubt that I'll be there to see it. Then, of course, I have a little aphorism there, but that's not what I'm going to deal with now. Oh, this one. Okay, but now I'm going to take you a little bit into the inflationary aspects and try and give you an idea of how profound our subject really is, the cosmological subject, because essentially all of physics is in this subject. And in particular, all aspects of quantum mechanics are expressed and writ large in the universe. And so at some level, this is a tale of 4 Plancks. The first Planck is the Planck satellite, from which has delivered so much information, and I've been involved in for a ridiculously long period of time, since 1993, and it is coming to the end of its story, but it seems like the story never ends. We're still working on a number of the papers. But with that information and other information, we have, in my view, well decoded the role of Planck's quantum h bar. That's the second invocation of Planck. And a third invocation of Planck is that Planck's quantum leads to quantum fluctuations, which are just natural. They're here in this room all around us, but they are the things that cause the structure in the universe to form as we see it. And a really excellent description of that mathematically is quantum diffusion, the Fokker-Planck equation, and that's the third invocation of Planck. I will say more about that as we go, but it involves a diffusion coefficient, which is involving h bar once again, the Hubble parameter of the universe, and that's the Hawking temperature. And so built into this is sub-h. It doesn't mean sub-Hubble, it means sub-Hawking. And when did all of this occur? Well, it seems like the natural epoch is in fact the period not so long after the Planck era, which is an energy scale associated with the Planck mass that is related to Newton's constant with h bar and c entering. And that's the epoch when we expect, if not before, that the manifestation of quantum gravity will have occurred. And of course, we don't know what to do about this, and I'll play around with that, hopefully stretching your mind a bit as we move along. But I'm going to go back to the microwave background first. There was the celebration of the 50th, I mean, you could argue that it was actually discovered back in around 42 in Canada, rah-rah, but the Penzias and Wilson paper was 1965 when it was published. And so there was a gathering, what is in effect the CMB family. Not everybody was there, but there were a huge number of people. I'm not going to go through, I'm going to show you various people a bit later, but it was the reunion of all of these people who've worked on many things, and it was also in celebration of Jim Peebles, another Canadian, his 80th birthday. I'm going to just list very quickly. I know that you know this, but why not say it again? Alpha, gamma, whoops. Alpha, whoops. Come on. Alpha, gamma, and Gromov and Hermann in the 1950s predicted the CMB temperature to be about 5 degrees Kelvin. And the discovery which they tripped over was Penzias and Wilson. They were great experimentalists, to be sure, but, you know, Dave Wilkinson should have gotten the prize with them, if not him, certainly Dickey. The CMB dipole, our motion within the cosmic microwave background, was discovered in the 70s with a relative temperature going like the V over C of our motion. And then what I'm quite proud of, and you're going to see a little snapshot of this, in 1987 we had what is generally regarded as a seminal meeting in the subject. There had never been a get-together of the CMB theory and experimental community. In fact, there wasn't much of a community then, but my good friend George Estathiou and I were had done a whole bunch of theory calculations, and the time was ripe to interact strongly with the experimentalists. And so I got Dave Wilkinson to help me draw in the experimental crowd. And you'll see that we knew a lot in 1987. We just didn't have the data, but we had a lot of theorizing that was going on. COBE was launched in 1989. That was the second CMB satellite. The first was Relict in Russia. Seeing the great Sinyaev here, and here. Where is Sinyaev? You can see him. There he is, right? In the center of everything. Black body was shown in 1990, not just by COBE, but also by a University of British Columbia rocket experiment, which was just quite an amazing accomplishment. The anisotropies were announced in 1992 from COBE, large scale, And at the same time, we had already made a discovery. There was clear anisotropy from the South Pole, Phil Lubin, and we also had it in the what is now called the FIRS balloon experiment. So the subject was ripe, and it all started to flow fast. We started to fill in all of the different areas of angular scale of seeing the microwave background fluctuations. And I highlight here the launch of the boomerang balloon experiment, which used quite accurate bolometers, because it was a bit of a breakthrough in terms of the way the analysis was done and the map that was given. Not that the other experiments weren't really great, but boomerang is generally considered to be one of the milestones. WMAP was launched in 2001. One of the most famous pictures of all time in cosmology is Sunyaev, Wilkinson, and then this young pup, me, in front of I think it was an Atlas rocket or something. But anyway, it's been much used. It was a really great experience. Polarization of the microwave background, which was long expected and well calculated, if I do say so, was revealed in 2002, first by Daisy and then by the Cosmic Background Imager, which I was part of, and Boomerang shortly after. In 2009, the Planck satellite launched. I may as well tell my little anecdotal tale here, since somebody who worked with George Estathiou, my good friend, we were side by side in the launch, and it was in French Guiana. Satellite goes up, the rocket goes up, and it looks like it was veering off. And so George, of course, on the edge of his seat says, "Well, that's it, Dad," because he thought, whoosh. But anyway, all was good. We got really positive statements of how things were going immediately after, and a good time was had by all in French Guiana. And then we waited a while. The first scientific results were 2011 in sort of a burst of first papers. Then 2013 and 2015, 2018, continuous stream, huge number of papers, huge quality science, really successful. And, you know, anything that can go wrong will go wrong unless you're incredibly careful to every detail. So all kudos to the experimentalists. Oops. Planck, 2015 to 2018, precision parameters, but also the precision parameters from the Atacama Cosmology Telescope, which I'm also part of, the South Pole Telescope, achieving higher resolution, also targeting polarization, as well as Planck. The bicep Keck, of course, that's really quite famous, South Pole based, partly famous for a misstatement of what the results meant in terms of the discovery of primordial gravity waves, but nonetheless, we should celebrate how remarkable that experiment has been in terms of the precision that was achieved for polarization. So the combination with Planck, which had, of course, fundamental information for it, has played an extremely important role in trying to constrain the level of gravity waves, and that is an ongoing thing with many new experiments trying to go after that as well. The future involves the so-called CMB stage 3, which we're in now, and that includes advanced forms of ACT and the South Pole Telescope. This is going to evolve into, for me anyway, the Simons Observatory, which has gotten a lot of funding and is a really ambitious experiment that will be keeping me busy for quite a while. And also I've been involved in SPIDER, which is for many, many years, which is also a polarization. It was sort of the sister experiment, except that it's balloon-borne to bicep Keck. We had one flight that was quite successful, and another flight is supposed to happen next November or December, but you never know what happens with the current administration in Washington. No more on that. CMB stage 4, it's going to be delayed to greater than 2025, but it's really ambitious. In some respects, it's a direct follow-on of Simon's Observatory. I was just in Japan for a period, and I just missed yesterday a telecon that we had because we got a study group in Canada to see if we can convince the Canadian Space Agency for us to become part of LightBird. LightBird is a Japanese satellite that, you know, I think it's all systems go, but you never know what will happen with funding situations for satellites. It looks like the Europeans are going to get involved. America is involved at some level, a reasonable level, and it's an ambitious space-based experiment. There are other satellites proposed. You'll hear, those of you who are hanging around next week, we'll hear about some of that, the American plans, et cetera, but this is the one that's the most likely, and look at the date we're dealing with there. Okay, so that was sort of a general diatribe on CMB, historical state, going through the things. Now I'm going to go back into a few more prosaic things, but it's all really quite fascinating. The inventory of the universe, usually you see this in the form of a pie chart, but I'm just going to talk about it in terms of a list. And the thing that we're going to most focus on here today is the stuff in gray here, which involve the relics from the inflationary regime, the ultra-early universe. Okay, we have the photons. I think I don't have to go through this in detail. I think, especially since this is a group which is here for a cosmology school, not everybody, but many. So I don't have to go through this in much detail. There are some neat numbers here that we should all bear in mind, but that's not really the topic. That is to say, the constituents of the universe are not really my topic here, even though they're absolutely fundamental. The only thing that I will point out briefly about the dark matter is that, of course, hot, warm, cold, that whole story, cold dark matter seems to be pretty good. There's no real contradiction against it right now, which means that it began life with a very small velocity dispersion. There are other possibilities. It could have a bit of warmth to it. That is to say, there could be a primordial velocity dispersion, which smooths things out a bit. One of the most entertaining possibility, actually, this was something that radiated out of CITA as well by Kaiser and Widrow, but it has been picked up a lot lately, which is that maybe writ large on the sky, not just all of the structure in the universe involving h-bar, but it may play a fundamental role on dark matter scales in which the fundamental unit is h Planck divided by m. That's got the unit, m being the mass of the particle, in this case a really, really, really low mass bosonic particle. And the units, you probably won't work it out in your head, the units of this are diffusion, length squared over time, and then the issue is that there is a diffusion length that would depend upon h-bar and the mass of the particles that would be there to be observed in the sky by looking at things like dwarf galaxies, especially at high redshift. But there are all sorts of tests that can be done. It's really, really fun physics. And we're heavily engaged in it, but it's not the topic. Cosmic neutrino background is there in number density about the same as the cosmic photons, and it's really fascinating. It really can have lots of information about the nature of weak interactions. The trouble is, it isn't so easy to observe the cosmic neutrino. See? What you can do is observe its effect on Big Bang nucleosynthesis, but it's really a sledgehammer trying to go after things relative to the absolute precision instrument that the cosmic microwave background is. Okay, that now takes me into the relics from the ultra-early universe, which don't have energy densities as high as this. I'm going to use the word phonons. Energy density phonons is essentially what the structure in the universe is being made of. You may say and I know many of my colleagues think, how can you use the word phonon? Phonons are only things that happen in crystals. That isn't true. It's any collective mode associated with density and can involve energy density as well. And that's actually what the inflaton is. It's a phonon in the ultra-early universe. Whether you can relate it to a fundamental scalar or not, that's a secondary question. The primary question is that it's a phonon, but because of the way gravity and matter entangle with each other, you can look at it in a completely different way and think of that instead as deformations of strain. And I'm going to play that story for you as we proceed through this talk, because I think it's quite a nice and novel way of looking at things. In this case, both the Planck scale and the Planck mass are playing an important role. So the inflatons are essentially related to the phonons. The gravitons, of course, it's the spin 2 quantum of gravity, and transverse traceless. The energy density is, of course, really, really tiny, especially from the ultra-early universe of the gravitons that are being produced, but it also involves as a fundamental aspect of fluctuations associated with H. Planck. Without H. Planck, there are no gravity waves to discover. There is no tensor to scalar ratio. Then there are all of the other degrees of freedom that exist in the ultra-early universe, which we don't know what they are. But, you know, we try and make the inventory, and ultimately it has to connect to the standard model of particle physics. These generic degrees of freedom, you might call them isocons, in the sense that they are not the inflaton, they don't involve the phonon, they don't involve that direction. They involve perpendicular directions, but there could be arbitrarily many of those that could have observable consequences that we are in quest of. So just as there's a standard model of particle physics, so there's a standard model of cosmology, and I think you probably know much about that, but we want to go beyond the standard model. We want to discover more things. We need more information than the information we've gotten, as I've already mentioned. At the risk of boring you, this is to get you used to the standard kind of maps that we look at with a microwave background, this being the Earth, South North Pole, you know all about that. I will be coming back to that, believe it or not. Milky Way, just to give you an idea of how things go, but everybody's enough of an expert here that that's just kind of superfluous, but let us just remind ourselves of the huge halo of dark matter that surrounds where the shining light is in galaxies to stabilize it. This is a fun figure. One could show one of the modern maps like SCSS survey, DES, or whatever, but we have to remember where we came from. Rashid will remember where we came from, which is that throughout the 80s, a little bit in the late 70s, all of this emerged. This is what is, you might call, nearby, our little neighborhood. It goes out to redshift 0.1, which means it's 0.1 effectively of an E-folding. And it shows already all of the basic elements that we use in describing the universe, namely clusters, clustering of clusters, superclusters, voids, and filaments. And in those days, as each one was eked out in a very complicated manner as time went on, each, of course, had its name. So here, of course, is the famous Coma cluster. Here's the Virgo cluster. This is not in the form that you saw it before. The North Pole, North Galactic Pole is up in this direction. This is the so-called zone of avoidance, which is the plane of our galaxy. This is one of the great superclusters on the sky, the Shapley concentration. I'm showing that for a reason. When I first became an assistant professor at Stanford, I had to give a talk, and the hot story of the day, and I'm taking you back to sort of 82 or so, the hot story of the day was the great discovery. It made headlines all over. the discovery of something called the Boötes void. Here's Boötes right here. It's actually a cluster, but this is the void. And this was really exciting in those days. And that was way back when. So we've been playing the evolution and development of the cosmic web since that time. What became clear to me, well, to lots of people, was that when you thought about the evolution of nearly Gaussian random fields under gravitational instability, there was a natural interconnectedness which occurred. And so now we have so many examples of that interconnectedness in the cosmic web that we don't really give everything names anymore. But there is still a bit of a joy to give things names. And in particular, recall Shapley here. And I'm going to, this has got really nothing to do with my talk, but I couldn't resist. Those who are Indians know that about 100 million people are going to pay homage to the Ganges and this river as well over the next 6 weeks or so. I call this the Indian Supercluster, and it had been discovered before, but it was really fleshed out by an Indian group with these illustrious names associated with it. The Shapley is at 0.045 of an E-folding back in time, and this is how it looks in Planck, and using an effect that happens to have it. Let's see, it's Zeldovich and somebody else. What's the name? Somebody else. Ah, that guy. Sunyaev-Zeldovich effect, the thermal, the hot gas booting up the microwave background, giving it a bit more energy, and that's what one's seeing. This is supposed to be a supercluster at 0.25 of an E-folding ago. Oh, you can't see it though. There are all sorts of dots here, dot, 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 that are supposed to be members. This is the Planck map superimposed on it, and you can't really see it except for the two largest clusters. In other words, the Sunyaev-Zeldovich effect is not such an easy thing to do. It's become one of the major discovery things of our time with the new microwave background experiments like ACT and SPT and Planck for that matter. But you can't flesh out a lot of information on the supercluster. Anyway, I just thought I would do that because it's here we are, and it's got the name of a river. Okay, again, at the risk of boring you with things you already know too well, but we're going to do it in E-foldings. We're going to look back from now. The light we observed, the light was released at 7 E-foldings ago, decoupling. Galaxies formed about 1 E-folding to 2 E-foldings ago, most of them anyway. There were no galaxies about 3 E-foldings ago. Light nuclei were created about 21 E-foldings ago. We don't know when the dark matter was generated and decoupled, but it might be somewhere between 20 and 35 if it's the so-called weakly interacting massive particle form. Almost all of the entropy of the universe was created at the end of inflation about 67 E-foldings ago. And then there's an epoch which may go to a very, very long way in the past, but from 67 E-foldings to maybe 127, maybe much, much more. That is the regime where quantum noise is determining what happens, and we'll see how that story is going to play out as we proceed. I did that. You see there's an average value of the log of the expansion factor, but the expansion factor is a very versatile thing, especially if you extend it and think of it as a tensor with an isotropic part, which is the thing you're usually used to, although you probably really aren't usually used to thinking about it as a something with spatial fluctuations, but it is really describing the universe. But if you also give it tensorial properties so that it's a response to initial positions what final positions are, take the log of it, then what we have is the, whoops, geez, now what happened? We have the average value of log A, and then we have the deviation from it. That deviation from it is a strain. And so that's this epsilon ji. And so I'm going to give you a little diatribe about the universe as a system under strain. The time derivative is, of course, an anisotropic tensor, a shear tensor. It's also called the Hubble parameter, or the Hubble tensor. And general relativity is all encoded in that description. It's just that it's sort of, in a sense, more intuitive. It involves a adjoint where A is the tensor. Okay, so now there is actually method to my madness of showing you the Earth, because there's a relationship of the Earth under strain, which leads to earthquakes, seismic waves, sound of various forms. Isotropic strain is sound. Anisotropic strain are shear waves. The universe is under strain. Spacequakes are things that generate gravity waves, and of course that's been the exciting period recently. With the Earth, there's elastic deformation, scale deformation, which is basically a deformation as well. Here, there's anisotropic strain in the universe. There are, as the analog of shear waves, gravity waves. You say, yeah, but wait a minute, it's not propagating through a medium. If you think the vacuum is in a medium, then you haven't really embraced the modern theory of quantum field theory. Isotropic strain is sound, and that's why sound is going to play an important role. I'm going to ask you to appreciate something that, because you know it so well mathematically, you probably haven't really fully intuited the remarkable thing that we say, which is that light and gravity are more or less fully entangled. And wavelength stretches under space strain, that's redshift, et cetera, bending of light, et cetera. But the fact is, we take it for granted that we use co-moving quantities, but that co-moving quantity means that at each little step, gravity is doing its thing on light, and that is what's happening in the evolution of the universe. That's a highly entangled system, and it can be broken, and it is broken, but throughout most of the evolution, it turns out to be all right. So along the same aspect of entanglement with gravity, I want to give you an idea of the way I'm thinking about inflation theory these days, which is rather different than most people think about it, because you usually say, oh, it's 0-point oscillations that give rise, and you know something about that in crystals. But if you really think about what these things are, it's a remarkable thing, because what it's describing is that the vacuum is something which is being deformed under the strain. And the strain is changing. Therefore, the vacuum is changing. That is an amazing phenomenon physically. And my view of the way to think about that is that there are the quantum fluctuations, which are all around us here in this room, but also in the ultra-early universe. But then the quantum fluctuations, we usually say they freeze out. But in fact, what happens is they're basically going unstable at low momentum or low wave number, and they form a condensate, so that the expansion of the universe, that's why I put an x and t in log A and considered the anisotropic parts of it. It is a condensed system. And that's a really interesting description that covers much things. And now I'm going to really not blow you away, but remind you of something quite remarkable, which is, if we think about what gravity is, and it does show that there have to be corrections to the gravity that we're used to thinking about. And how can you not deal with those corrections if you're trying to think of the ultra-early universe? So elasticity, there is a relationship between stress and strain, and the thing that is the response function between the two, they're called bulk and shear elastic moduli, and it's just stress proportional to strain. Sound speed is bulk elastic modulus divided by the density. There's an anisotropic shear speed as well. Viscosity with fluids, it's bulk and shear viscosity, same thing. Strain rate. So what is gravity? Its stress is a bulk acceleration modulus times the strain acceleration. It also turns out to be the same thing times the tide. Of course, that's just a rewrite of Einstein's equations in many respects. But if you think about it, this is a constitutive equation that has a parameter in it, which is this BAM, the bulk acceleration modulus. That bulk acceleration modulus is 1 over 8 pi gn, which is m Planck c over h bar, related to the Planck scale. So in other words, gravity has to be corrected. The question is, how do we have the audacity to think that we can learn anything about the ultra-early universe if we know that this theory can't be complete? It must have corrections. It is like dealing with elasticity, which has corrections as you go to shorter and shorter scales, that these become k-dependent, for example. Okay, I've given you my little mantra about inflation theory and the way to think about it. And so the way, and this is sort of, new stuff, and we'll get back into the microwave background. So I'm just trying to take you and massage your mind a bit about some new ways of looking at things. There are stable quantum fluctuations whose momentum, h bar times wave number, is greater than the Hubble parameter with an h bar multiply. Those oscillate. Those are the usual kind of quantum fluctuations, except that we aren't really that used to knowing how to think about this, and we actually tripped over this a little while ago. Fortunately, Zeldovich and Starobinsky were there to tell us way back when how we should be thinking about it, because what you have to do is you have to get rid of the h equals 0 limit fluctuations, and usually that's done by something called normal ordering. I'm not going to get into any of the details of this, but there is a profound sense in the most important issues in physics is playing out in the ultra-early universe in terms of how do you treat quantum mechanics and curved space-time, and we're working on this quite a lot actually now at CITA. The quantum fluctuations become Jeans unstable as soon as the momentum, Jeans instability, meaning that gravity beats the oscillation aspect, as the Hubble parameter drops. And the idea is that as the universe develops, the Hubble parameter drops. I mentioned that one of the, I can't see that. What's that? Okay. Does that mean 25 to go or 25 to? Well, that's okay. I'm trying to give you a little trip here, and then I won't say we'll speed up, but I will get into more familiar ground. So I've invoked the Fokker-Planck equation, stable and unstable modes. There's a whole beautiful theory associated with this, and as I said, h-bar and Planck are playing an important role. Also, what's playing an important role is the energy difference between the fluctuations at a given value of h and those with h equals 0. That's called the Casimir energy in a generalized sense. And that is, at least as far as we can tell with the theory now, it is what the nature of the condensate is that is part of the inflationary development. Okay. But there is one thing that you have to draw from all of that little thing where I hope that you have a picture of really interesting physics going on back then that's really at the leading edge of our thinking. And that is that there is a parameter that I want to introduce. Whoops. Yeah, a parameter I want to introduce, which we call zeta. It looks like the S in Superman, and there's a good reason for that because its properties are similar to entropy. It involves d energy plus pressure d volume with an appropriate E plus PV normalization. It's actually an integral over different histories, but it involves this trace of alpha, which is the metric log of A, and d ln rho divided by 1 plus an equation of state parameter of the universe, which comes as pressure divided by energy, or PV divided by E. Just as with photons, entanglement is an extremely important thing, making co-moving aspects, which is actually like an adiabatic combination. So here, energy density and gravity are entangled through this quantity. And in fact, this is an adiabatic invariant. It is the best measure by far of the nature of the fluctuations in the early universe. And everything that we know about the early universe is encoded in what we've learned about zeta. And the rest of the story that I'm going to tell is to show you what that tale is. I would love to tell you the tale of what we learned about the tensor waves or gravity waves in the early universe, but I'm afraid we aren't there yet. Okay, maybe I'm going to skip over this, which is giving you more about the theory of inflation. Please do ask me about it. What happened there? Oh, I see. Was I supposed to play that? I think I'm going to skip over that. Well, it doesn't really matter so much. I mean, I think that given the time, I want to get onto the microwave background. Let me just say that there is an arena. It involves the evolution of fields in the ultra-early universe that takes us not just from the inflationary regime, but also through the end of inflation, the production of entropy, the production of heat, the production of ultimately standard model particles, so that we have actually a complete description at some level going from the condensate, how the condensate breaks up to make the standard model of particle physics, except that we don't really know how it connects to the standard model of particle physics. Those degrees of freedom are presumably there as the end of inflation plays out, but that connection eludes us, and so we make approximate cases for that. I think this is a movie, but it's a movie I'm going to skip over and go back. So now we're going to try and take that framework and relate it to what we've learned from the microwave background. So we're going back to this CMB at 50 meeting, and I've got circles around people. Who is that guy? Really young and handsome. Wow. That's Fukugita. That's Bill Jones, worked on Experiment Spider with me. That's Martin Rees, John Karlstrom, South Pole Telescope, Jean-Luc Pouget, the PI of the HFI instrument in Planck. This is George Estathiou, friend. There is that guy again. Oh, he's cropping up. I noticed that this character is here. That's Kluba, who you're going to hear rather too much from in the next couple of, no, joking. It's joking. This is Penzias. That's Wilson. Is that right? No. Sorry, this is a Nobel Prize winner. This is another Nobel Prize winner. This is Wilson. That's Wilson. That's Peebles. That's Lyman Page, who will, of course, be entertaining you as the time goes on. This is the famous picture where character here, but this is at the launch of WMAP. That's John Mather, Kobe. This is John Kovacs, who's Bicep Keck. I only, there are a whole bunch of other people, all people I know really well. It's been a fabulous experience as our field has matured and developed. This is Andrew Lang, unfortunately not with us, but he was fundamental in developing the bolometers for Planck and for bicep Keck and for Spider. Fabulous character. Here is just a snapshot of the many ways that we look at the data from the sky. These are the ground-based ones. This is balloon-based. This was a Spider flight, and we have another one on tap. Here's the site of Simon's Observatory. This is Atacama Plateau, and that's ACT. It's another experiment. CLASS, which is just starting to get really great data now, is right up in this. This is in Chile. This is Polar Bear, also nearby. They're joining together to become this Simon's Observatory, and ultimately that's going to grow both at the South Pole and at Atacama into CMB stage 4. But there are other experiments floating around of great interest, which I won't go into, but I will point to the ones at the South Pole, BICEP, and the South Pole Telescope, which is, looks like I've conveniently hidden it. And this is Keck. BICEP and Keck sort of go hand in hand. Okay, so then there are the balloons, and then the issue is, are we going to be able to go back into space? Like with large-scale structure, the number of people that are engaged in these experiments now is really large. And so this is just institutes. These are the Planck institutes. These are Spider institutes. These are, this is advanced ACT institutes. And so what this means is that all of these issues have become management problems, and for the young people in the audience, you have to find your way within these really large consortia in order to find something that you can put your personal stamp on. But on the other hand, it's extremely rewarding because the data is just flowing fantastically. Okay, I think I don't have to really remind you of these things. I think it's a bit of an extra. Here's COBE's resolution, which is 420 minutes. WMAP's resolution, best resolution, was 12.5 minutes. Planck was about 5 minutes to 7 minutes, depending upon what the frequency was. But the higher resolution experiments like ACT, SPT, were like 1 arc minute, a little above. Here's just some snapshots of other maps of the sky, smaller size, but showing, for example, here, Planck and ACT, that ACT with its much better resolution sees things. You see the same things, but you see it with much more precision in ACT. And you get the little dots here, which are clusters of galaxies that you can't see with Planck because of its beam. Oh, this isn't working out. This was supposed to be quite beautiful. It is a streaming figure. I should turn this around and show it to you, but the colors are all screwed up. It's showing the combination of Planck and ACT. So this is sort of the highest resolution and largest scale that one can see, but that's enough of that because the colors are all washed out. But there are all sorts of clusters, the Snezhevich effect, and other things in the map. Okay, so this is the total temperature intensity when you've taken out the dipole and the average monopole, and it was unveiled, and this is the most recent 2018 map of Planck, and you know, it's got the usual ups and downs with the temperature change, which I won't try and describe in great detail. It also doesn't come out very well in terms of color. This is with the polarization superimposed, and so there is a relationship, a correlation between the polarization and the total intensity, which we've used to very good effect. This is something else, which is that you can take the data and go to high precision. I think you've had talks about this over the past week or so. This is a map, believe it or not, of the projection of the gravitational potential, which is the lensing potential, which takes the photons, remember, they're highly entangled, and it describes how they're all bent, and that's the data we draw from it, which is really 40 plus sigma detection with Planck, but also ACT and SBT have also done major things with okay, if you spherical harmonic transform these things and make the appropriate power spectrum, you get the usual thing that you've seen ad nauseum, which is that this is the theory curve and this is the data, and this is actually the size of the error bars on the data, which you can't really see. It's an amazing, amazing thing. The emergence of that was quite remarkable. Okay, why isn't that? Now we can't even hear it. What you're supposed to hear right now is you take that and you compress it into something that has a sound associated with it. Not a very pleasing sound, you might say. But you can see that there's more structure than just pure white noise. It's the sound of the machine. It's running the universe. Anyway, that's quite fun, but completely useless. Okay, I was going to show you where we come from. This is the temperature. These are power spectra of the same sort in polarization, two modes of polarization, that we've got this information on the so-called B mode. The level we're dealing with here relative to the discoveries of the temperature fluctuations of the microwave background, look at the number of orders of magnitude on this. And the fact is, we've got these error bars on this. It's just amazing. So the story has been fantastic. And this is the gravitational potential lensing, the 40 sigma detection. But look at that. It's all, and it's going to get so much better. I could wax eloquent about how it all emerged in time, because we actually knew a lot, even a long time ago, before we got these experiments. I mean, obviously, Planck has been a breakthrough, but so was WMAP, although it didn't go nearly as far. I told you that there was this great meeting we had in Toronto in which many things were discussed, but I think I'll just skip over that. It was just that what was on the table back in 1987 is still very much on the table now, and almost all of the ideas have still been I keep pressing that and it's fine. Well, it's supposed to go forward. Okay. Okay, so now I will get to putting it all together, putting the temperature information, the polarization information, to make, and you should be quite impressed with this, except that the colors don't come out very well. This is actually a map of the ultra-early universe. This is zeta. This is that quantity, this adiabatic invariant that characterizes the metric fluctuations. It is the map of the isotropic strain of the ultra-early universe. And you'll see that it bears some similarity, but not as much as you might expect with the intensity. And the reason for that is that it doesn't have baryon acoustic oscillations, because the early universe, ultra-early universe, didn't know about it, and so this takes it out. And this is this value of zeta subject to this constraint. Of course, you know that there is no such thing as a map. There is a map ensemble. A map is a map plus fluctuations. And if you don't know about the fluctuations, you don't know about the map. Of course, when I showed you the map of the Earth, the fluctuations are pretty tiny unless you go to really high res, so you don't notice it. but with the microwave background is absolutely fundamental. So I want to draw your attention, let's draw your attention to this little thing here, which is corresponding to what's called the WMAP cold spot, except that this is reflected in the ultra-early universe, and there are also some anomalies here. And this is what happens when you add sort of a random fluctuation that's allowed by the data. And the idea is that this is a mean map, an average map, sometimes called a Wiener filtered map. And these things tell you what you can believe or what you can't believe. And if you go back and forth, is that mine? All right. Yes, so Planck somehow came back. No, stupid. Okay, what have we learned? Well, you know what we've learned. We've learned that this map and things that we can derive from it in various better statistical techniques has allowed us to characterize the complexity of the ultra-early universe in terms of one thing, that it looks very much like it's a nearly Gaussian random field, which is one that is characterized by an isotropic power spectrum, P zeta of k, but not only that, that power spectrum is characterized by an overall amplitude and a slope. Well, you know that really well. That's one of the great success stories. The great success story, the thing that has been highly celebrated with Planck, is the value of this spectral index, which one is scale invariant, is decidedly not scale invariant, and it is 8.8 sigma from 1, which is scale invariant. So this is an amazing thing, that this number, but that's not all, as we will get to in a second. That was our fluctuation thing. And before going into the grand result that we are moving towards in terms of the characterization of the ultra-early universe, I do want to point out a few of the anomalies. I had a whole list of the anomalies here, the things that don't quite look like the two numbers story. So this was this famous cold spot that I was talking about, but there are also larger scale anomalies. They have the disadvantage of passing through the plane of the galaxy, which means that you have to be really careful that you don't have galactic contamination. But after many, many years of working hard on this, we think that these are really solid. The trouble is these are large-scale things, and there is something called sample variance, which means that you roll the dice again, and these are not really multi-sigma deviations. They're only about 2 sigma deviations. In particular, there's this famous WMAP cold spot, which has a well, anyway, I won't get into the details of what it is, but it's basically a 4.5 sigma fluctuation, which means that the probability of getting it, if you throw the dice 100 times, is an order unity. It's got a characteristic scale involving a multiple number of about 20. And there have been people that have claimed that there is something that might be associated with it on the sky that's nearer than the microwave background surface, but that just doesn't seem to be very likely. But maybe there are explanations that can come within the context, which actually, if you come to my talk next week, if you're around, I might even talk a bit about. Anyway, this is an anomaly. It's an anomaly which is a real anomaly. And the question is, what is it? And we still don't know. Oh, brilliant. Okay, what am I doing here? Oh, yeah. Right. Okay, so this is just to show you. See, here it's in red because it's a little log A bubble, a little scale factor bubble, really tiny. And so I press this thing. It's not going forward or back. I think I should just do that. Okay, anyway, what you can see is that in the temperature data, it's there. You can't really see it in polarization. You haven't seen those results from Planck yet, but the paper's about to come out. I'm going to forget about this. It's much better to just do it. Okay, so you don't actually see it with a lot of clarity in polarization, but that's sort of as is expected. So this is the second most important, well, this is the most important figure of all. Which is, instead of looking at things in terms of a map of the sky, we're going to look at it in terms of a quadratic map, otherwise known as a power spectrum. So this is a reconstruction of the power spectrum of zeta, and apart from the fact, as I said, it looks like a Gaussian random field, so every information about the early universe is encoded in this. What one's done is an expansion in bands where these little triangles are, and you allow the amplitudes to float freely, and the question is, what is the data delivering? And what is absolutely amazing, so when you go to this end and this end, you start to have problems with sample variance or noise, but in the in-between region, it looks like a straight line. It looks like a uniform NS is absolutely spot on. And the value of that uniform NS, which is the best fit from Planck, is that line that's going through there. And this is with all of these degrees of freedom being added to the data. In other words, it's a triumph in many respects. It's too bad that there isn't something more to discover in it. There are no ups and down oscillations or anything like that, which we've looked for in the data but haven't found, except there is this little anomaly here that's associated with something that you can see in the temperature spectrum, and it translates into something that involves the ultra-early universe. But statistically, the amount of power in that band relative to this, which is the standard model of cosmology, it's minus 0.26 plus or minus 0.13, and that's just in this data point, this band, and the other bands are easily within the 1 sigma, very much so, for all of the other bands. So this is like 2 sigma, but just 2 sigma. And it went down a bit with the Planck 2018 data than before. Part of that is because we filled in more of the information. So this is the thing that is actually telling us that 2 parameters are sufficient to encode the overall amplitude and the slope, and that in spite of this, it's not statistically significant. The trouble is we will never, no matter what the experiment, we won't be able to really improve upon this. You might have expected that the polarization would come to our aid. This is the L analog of the wave number. Why doesn't it? It's because it's a conspiracy. It's a cosmic conspiracy. It turns out that the polarization power spectrum is low in amplitude in that regime. So you don't get a lot of extra information in that regime. So we're stuck with this, and the likely situation is when Lightbird flies, when all of these things happen, we will get more or less exactly the same thing back out. And if we don't, we will have found that there was an error in Planck, but I don't think there is. WMAP saw much the same thing. So there it is. That's what, you know, our future looks like. 1,000 years from now, people will say, is this anomaly significant or not? Anyway, it doesn't do us much good. But we should celebrate. Now, the other thing that we should celebrate is this, which is the 2 sigma and 1 sigma constraints on the tensor to scalar ratio. So this is the power spectrum in tensor. Now, you just don't have the ability to throw a lot of bands at it. So essentially, you just give it a slope and an amplitude. And the slope is, in fact, constrained. But what happened when we went from bicep Keck 2014 to bicep Keck 2015 is that this went from an upper limit about here to an upper limit about there. That is to say, there wasn't a lot of value added. But what there is that with all of these degrees of freedom that were allowed for the spectrum of zeta, of the primordial scalar anisotropies, even with all those extra degrees of freedom, you essentially get the same upper limit. And that upper limit is really impressive. It's 0.06. Our future, if we believe our forecasting, and you have to take it all with a grain of sand, but salt or whatever it is. But the forecast, including attempts to get rid of the dust signals, which are clear contaminants here. Simon's Observatory at 1 sigma level is supposed to get to a value of around 0.0003 error bar. CMB stage 4 about 0.0005. Lightbird 0.001. So there's a lot of effort which is going on to try and push down this limit with very high precision experiments. Okay, I was going to show you some the other most famous figure from Planck is the tensor to scalar ratio against tilt and how many models are ruled out, but I will pass over that. I'm sure somebody's going to treat it. It's actually -5 or +5? What? What is it? I do? Okay. All right, so maybe I will say something about this. Okay, this is where we are right now. This is where we expect to get to with Simon's Observatory in terms of the kinds of limits. Of course, we assumed a simple spectrum without the anomaly in it. But the thing to bear in mind is that relative to Planck, we are going to improve this power spectrum a lot with really quite tiny error bars. And so one of the things that with the high resolution you can do is you can push this way. Why am I emphasizing this so much? This is the compression of all of the information from the experiments about the early universe. This is it. This is what you get. Nothing else. Our hope is that buried somewhere at the really subdominant level are some indications of non-Gaussianity in the scalar spectrum, or maybe some indication of modes, which I called isocurvature modes or isocons, which are perpendicular to the inflaton direction. So far, all we've got are upper limits, and similarly for the tensor to scalar ratio. So there's no indication that any of that is there, but you know, we are going to reach the precision not just to improve on zeta, but to improve on those limits. And let's just hope there's a discovery space to find something. So once again, let's go to this RNS figure. And, you know, one could wax eloquent on the different models, but none of them are spot on. And the attitude I think that one should have is that our approach to inflation is a phenomenology. There is a holy grail to the subject, which is that we will develop, and the terminology of the game is that at the high end, as we approach the Planck mass, you want the theory to be so-called ultraviolet complete. And at the low end, you want it to be infrared complete. The infrared complete is perhaps manageable because it will be the connection of the end of inflation to the standard model of particle physics. The upper end may be just a fantasy of theorists that given the little bit of information we get about the universe, that we can actually come up with a fundamental UV complete theory of everything from, I mean, it will be informed by the data, but it will be a piece of luck if humans can actually pull this off. At least that's my view. So there's a lot to be said for a phenomenological approach. There are some headlines that one can take away from this diagram of tilt against tensor to scalar ratio. Uniform acceleration as one passes through the inflationary regime is strongly ruled out. various sort of natural laws were ruled out. Models that I'm actually was quite associated with are highly constrained or even ruled out. There are a whole class of models that begin with the ancient Starobinsky model, which was really the first inflationary model, that are still actually valid and give us a target to go for with R. These are special kinds of models. Not every model can give a tensor to scalar ratio that is at all discoverable. We've certainly worked on models where the value for R comes out to be 10 to the minus 10. And in fact, there was a time when we thought that that was sort of the standard that we would get. Okay, this is a forecast. Oh, come on. Can you just get it up again? We'll go to the next one. Okay, so that's the end. This is sort of where we're at in terms of what we've gotten from the universe so far. We've got zeta from inflation, observable, amplitude slope. From it, you can derive an acceleration history and an effective potential over the small regime that we get to probe. No big surprises, it turns out. We have a mechanism that can generate entropy. It's getting exactly the right value, which is 10 to the 88.6, the entropy in the known universe. We can see it's almost all in the cosmic microwave background and the cosmic neutrino background. Relic 3 is the baryon asymmetry. We don't have a complete model for that, but we certainly got ideas, been working on that for almost 40 years. And so, you know, it comes and goes, and it's got that interesting number 10 to the minus 10 for the baryon to total entropy ratio. Dark matter, well, we've been with dark matter for a very long time and still don't really have a very good idea of what it is, a lot of effort. Big Bang nucleosynthesis products, that's been one of the great success stories, and how the microwave background, the symbiotic relationship between observing the elements and the microwave background, how it all fits so perfectly together is obviously one of the fantastic stories. And so, you know, it gives one a great deal of confidence. Microwave background, of course, with all its fluctuations and polarization, galaxies, and large-scale clustering, best important thing, you've heard lots of talks on that, it's not the dominant one here for me, was the large-scale clustering adds the extra dimension of tomography, that is to say the redshift direction. And then dark energy, and if one were in a praying mode, one would pray for A, let's hope it's dynamical, so that it's more than just lambda, and even better, that it's coupled to other matter, so that there is something that will give us a lot more information about its nature. For example, its effect on far outskirts of clusters and galaxies, etc. Otherwise, we aren't going to get, in spite of the billions of dollars that are going to be spent, not very much information. These are the relics that we haven't seen. I'm not going to go through this list. It's just that there are lots of possibilities that could come out of the ultra-early universe that we are in quest of. This is all beyond the standard model physics. And the anomalies may end up teaching us something. The way the world goes is you start with an anomaly and it keeps developing, and then it becomes, oh, that's real physics because you've figured it out. The trouble with the CMB is that you're in this sample variance issue where you just don't have enough modes exhibiting the anomaly to be able to say it's not just the statistical chance. Large-scale structure adds the ability to do this a lot. And then this is the executive summary, which is the map, the picture of the ultra-early universe that we've derived from Planck and other things, but mainly Planck. We had a similar thing for WMAP a long time ago, but this is much more precise. The spectral index, 8.8 sigma, that you don't need to assume uniformity. You still get the same value for NS. And for the tensor to scalar ratio, you can still add lots of degrees of freedom and still get basically the same limit to the tensor to scalar ratio. And the future for NS2, but in particular for R, looks extremely bright. and let's just hope that we are going to be able to, that the universe will have been delightful enough to give us an R that's detectable, because it could be really low. I told you about the 10 to the minus 10. So then the microwave background and large-scale structure are, in fact, a fantastic fundamental physics laboratory, not just for the ultra-early universe, but also for features like neutrino properties, et cetera, masses, and number of relativistic particles, and et cetera. And so we have a tremendous future. One wonders whether the game is almost up because everything has sort of fallen into place by a standard model that's more or less been around since '87. But because of the tremendous investments that are being made, we're hitting such a level of precision with this that something is clearly going to give and be unearthed. And even if we don't get anything more out of the ultra-early universe, all of the secondary science we get out of microwave background research is enormous. So I hope you all engage in that subject and are here next week. Anyway, thank you.
Okay. Yeah. Sure.
Anomalies at length. You talked about anomalies. So what is your take on posteriori nature of statistics that is used to establish the significance of these anomalies?
What one does is exactly what one should do, and all of the people that invoke the look elsewhere effect, I think, are all crazy. That is to say, the classic thing that has been done is that one has, in effect, done some kind of a renormalization group kind of thing. I mean, if you decided that you would make the sweep of filters, for example, have really complex shapes so that every little bit of the data, you could actually just fit it. But what has been done is that you have, for example, wavelets or some kind of way of looking at the data, and you're looking for something that will be real if you find it, because there is information at every harmonic scale, and if you find something, then it's there. Then the question is, what can give rise to it? And people say, well, if you don't have a theory, you didn't get to look for it. But that's just silly. You don't make a discovery that way. You have to try and look for what the data is delivering to you. You have to be careful, obviously, because you know, one of the things that, not in the microwave background, I might say, except for the report of gravity waves from the ultra-early universe, the microwave background has really not made any big errors. Large-scale structure, I can't say the same thing. Every now and again, somebody would say cold dark matter is completely ruled out by the following results. So you can find anomalies. So the real issue is, have you been able to simulate the kinds of things that you're going to see? Have you been able to put good statistics on it? And so that's why it's been so fundamental to make sure that we could put proper error bars on the anomalies that we've seen in the Planck data. And one of the fantastic things that was done, which was, I mean, it wasn't like we weren't doing this before, but Planck really pushed hard on trying to get end-to-end simulations, and lots of them, in order to get accurate statistical determinations of what the values of these anomalies are. What would make it much more compelling is if the different anomalies could all be brought together in one sort of grand unified theory of anomalies, all locking into some ultra-early universe theory. That has eluded us so far, that's for sure. It is clear that many of the anomalies are quite related to each other. You can see what it's doing it on the sky, but not all of the anomalies come under this. So for example, we tried really hard to find the origin of that dip in some kind of set of things that you could see on the sky, and it was rather a failure. So, so there is no sort of real space smoking gun to the anomaly in the power spectrum, for example.
Hi. General question. I heard about some somewhat unconventional ideas of trying to make a direct, reasonably direct measurement of the cosmic neutrino background. What do you think? Could you say more about?
Taken it seriously enough to have the people come up to CITA to tell us how it's done. There's somebody at Princeton who's pushing it, and it's fun. It's really hard. I mean, my thesis was on, one of the main things was on coherent scattering of neutrinos, and it's trying to make use of that sort of nice collective aspect to do it. But I don't know, it's going to be hard. I mean, it's fantastic to go after, but the interactions are so weak. Yeah, that was what we were talking about, Tully. Yeah, no, I mean, it's a serious effort, but it's really... Well, I'm glad somebody's doing it.
So this question.
Since we're talking about hard things, how hard do you think will it be to really reach these goals for the R in terms of control of systematics, foregrounds, and everything? In particular, from your perspective of having seen how Planck was initiated and has grown and been extremely successful, how do you extrapolate?
So in terms of nailing instrumental issues, systematics, I have no doubt we can do it. So then the question is, how complex are the foregrounds? And what's been done so far has not put all of the complexity that actually one expects in dust emission. The model that is generally used is sort of a gray body model with just a power in wavelength times a single temperature, and that's got nothing to do with reality. So that, in fact, the way dust works is there are multiple temperatures and probably just one index because we're at long wavelengths. So it goes like frequency squared, and because dust is tiny and the wavelengths are big, and that's what you expect, and that's probably the way it works out. So the thing that is phenomenologically fit is actually associated with multiple temperatures, and all being projected along the line of sight, and that has never really been taken into account. There are brave attempts now. Hensley and others are trying to put in multiple temperature, more than was done before, multiple temperature modeling of the dust. There are good correlations with the H1 in the galaxy that allow you to regress some of this stuff out. And so nobody knows where the floor is really going to be in terms of where it's going to be diminishing returns. You got to go for it. And there's no doubt that the best information on the dust is going to come from these experiments. And so it'll be a symbiotic relationship of interpretation of the data and trying to do it. I mean, I'm working on the dust aspect. It's actually quite fun subject in many respects. Dirty, but fun. Nobody knows how well we're going to be able to clean it out. You can see that one of the slightly disappointing things about the transition of Bicep Keck adding a lot more data is that the value of its R limit in conjunction with Planck didn't change that much. And yet there was a lot more data. And they have a lot more data still, but it may be that, the problem of marginalizing over the dust is going to be a real killer. Of course, people are trying to do the modeling with the forecasts of the dust, and we did it at CITA. And then the question is, yeah, but have you put enough complexity into the model or not?
Experiments. Okay, these are Simon's Observatory, where your institute is participating. This is 4, where you are planning to participate. And this LightBird, I think you already are participating. And my LightBird is space, CMB is 4, and Simon's are ground-based. And everybody in the world thinks if it is possible to do from the ground, it will be faster and it will be not much worse from the space. What you think yourself? I am a spaceman. I think that space is very important and must be clean. But numbers that CMB S4 will be in reality twice better than LightBird. What are the dates for all these experiments today? Could you remind us?
Greater 2025 for us, for greater 2028 for LightBird.
LightBird later.
And then Simon's is actually, it's the immediate follow-on, and we've already got the first, well, the first telescopes are being developed, so, I mean, being built, right? And so it is going to happen. It's going to happen during my productive scientific period. But
Canada now has no upper limit for...
But your point is, I think it's extremely important to bear in mind. So our target of these ground-based experiments is the way the spectrum looks for the so-called B mode of polarization is that there is a bump associated with recombination, which is great. It's around 80 or so, and you can really, I think, go, I mean, that's what bicyclics on. You're going for that from the ground. Then there's another bump, it's called the reionization bump, which is like L of 10-ish or less. Doesn't even matter if in your space that's really hard, but that's what LightBird can really add to the story. Obviously, the things have to be done. Now, the other aspect is that it's been really difficult to get 280 gigahertz to be accurate from the ground. And 220 is, you know, people are going for that too. So what you don't have is a really great dynamic range and frequency to try and get rid of the, that's why space is extremely important. But I will also be a champion for the balloon experiments, which are getting a bit short shrift rate now, but the advantage is they can be a lot cheaper. You can put them up fast, as long as NASA's prepared once again to take a bit of risk, because it's not like a space experiment, which is so expensive. And so I've been part of proposals. For example, there's B4, which what it was going to go after is R, but also the tau, the Compton depth, which tells us about reionization and the redshift of galaxy formation. You can, in principle, get that from a balloon, and it's a question of how well you can do. There is a claim, and it's being tried by the experiment class, as you know very well, that that you can go for this from the ground, but the L's are just so small, so much can go wrong. What we don't know yet is whether or not we can actually deliver with the big telescopes like Simon's Observatory and ACT. I mean, Simon's Observatory is also going to have small telescopes to go for the low L's, but whether we can actually deliver in trying to fulfill the R limits, like the Simon's Observatory limit, I think that's quite targetable from the ground. But really, the way it has to go, and I obviously will be speaking to the converted here, it's actually multi-messenger in the terminology. That is to say, we need the ground and the space and the balloon, because you've got to have the whole story and everything has to fit together. And it is fine to get some of the frequencies from experiments using different platforms. I mean, assuming everybody's done their job right, it's perfect. There's no, I mean, the way the microwave background developed was heterogeneous experimental data sets that provided the experimentalists were, you know, honest about what they were getting, it all fit together, and it did give a pretty consistent story. And I have no doubt that you completely buy into what I mean, that's the only way to go.
Dick, just not to be long, you talked about November flight of Spider. What is the last decision? How many frequencies it will take?
3.
3?
Yeah.
What
it's
is the
just
upper?
90, 150, 280.
150 and
280.
280, 218.
280.
280, 280. Okay.
Yeah, we aren't trying to do
It's very
anything, Senor Zadovich. So, but it's got a nice baseline, and the detectors look good. The problem is that NASA's screwing up its balloon program. Yeah. Yeah. Well, the thing that's frightening about Spider is that Bicep Keck has just been sitting there integrating all this time, right? So they have a huge amount of data, and look at the trouble they have. And we have pretty pristine, you know, good data, but not everything went perfectly with the first flight of Spider in terms of, you know, where we thought we could get to. So we're trying to correct everything to get a much better precision on the second one, but it's not easy. Oh, it's still about 40 minutes. It's not different. What I can guarantee is we'll get really good dust information.
It's great, though.
Well, actually, it's pretty interesting.
Any further questions? No? Okay, so let's thank Dick again.